Thanks a lot, Chairman. So first of all, I would like to thank the organizers. I mean, there is Ali Genser here and their team for having put together this wonderful conference. I mean, I can only imagine how hard it could have been during COVID times. I mean, and this is by far one of the best locations I've been to. So really, thank you. Thanks also to Sasha Golubov and the rest of the program committee, for inviting me. So, I mean, a lot has happened since I submitted the abstract for this talk, but I decided to stick, to the original title and basically talk about nodal exchange coupling between a ferromagnetic insulator, sandwiching in YBCO superconductor, so a nodal superconductor. As I said, about this, okay. So as I said, lots has been happening. I mean, I moved to Constance from Cambridge, where the work I'm going to present today was originally done. So this is my current research team at the moment, and we're working on a variety of new things. I mean, I just list them here in case we want to discuss for collaboration. So we work on 2D superconductor ferromagnetic structures, also on oxide superconducting spintronics. I mean, the field effect superconducting devices, which is a new research field in physics. And then molecule superconductor hybrids. But the work I'm going to talk about today basically is this work that I carried out in my last years at the University of Cambridge. So here are the people I've worked with. I mean, Jason Robinson was my supervisor, and then I collaborated with him for this work when I became independent in Cambridge. Then Saccio Komori and Giorgio Di Vitini that did the TM microscopy, and Saccio Komori was a postdoc in the same group. And then the group from the University of Salerno, so Mario Cuoco and his co-workers that put together the theoretical model. I mean, I'm quite fortunate regarding in the introduction of the field. I mean, fortunately, there has been many nice talks before mine, so I don't have to do it again. But as it was mentioned in the talk before, by Anatoly, so basically the field of superconducting spintronics has developed extremely fast, in the last years. And it's the main reason behind it is because it offers the potential for the development of low dissipation, electronics, working basically on superconductors. So the idea is basically to combine the two elements that are, on the one hand, ferromagnetic materials that are the key element of spintronic devices and basically superconductors. So that's where the name superconducting spintronics stems for. Now, I will not go into the details about this because you heard a lot of talks about this, but you know that when you have a superconductor and a stack of ferromagnets that you can also consider just as a single ferromagnet with a homogeneous magnetization, basically because of the exchange field at the superconductor ferromagnet interface, there is a spin mixing of these spin singlet pairs, and you end up generating a combination, if you want, of spin singlet pairs and spin zero triplets. Now, both these components of of the wave function, the Cooper pair wave function, are very short decay inside the ferromagnet because ferromagnet and superconductivity basically do not like each other. So this exchange field introduces these different, if you want, phase shifts for the two spins inside the Cooper pairs, the spin singlet Cooper pairs of electrons, and this induces a very quick suppression of superconductivity in the ferromagnetic layer. But fortunately, I mean, for us working in this field, there has been a few predictions at the beginning of this century, basically suggesting that if you now change one of the two ferromagnetic layers and you introduce some magnetic inhomogeneity, basically what happens is that is a spin zero triplet that is not rotationally invariant, unlike the spin zeros, unlike the spin singlet, can now be projected along a different quantization axis, and you end up generating these fully polarized spin triplets. So you can see now that within the Cooper pairs of electrons, both spins are aligned. So these ones now, I mean, are fully polarized spin triplets, and in principle can be used for spintronics application. So this was the beginning of the field, and then there is a lot of experimental work based on Josephson junctions, spectroscopy experiments, and so on to prove the existence of these spin triplets. Now, I want to make now a step back in my talk and understand a little bit why we have been talking about, also in the last two talks, there have been people talking about superconducting spin valve or pseudo spin valves. I mean, basically, I mean, what I said is that we are trying to do spintronics with superconductors, and of course, if you want the main spintronic device, the de facto, if you want, spintronic device is the spin valve. I mean, the spin valve stems from the giant magnetoresistance effect that was discovered by Fert and Grunberg at the end of the 80s, And what they basically discovered is that, I mean, they grew like some multi-layers of iron chromium, and in this case they realized that for a certain thickness of the spacers, in this case the spacers are the chromium layers, it is possible in zero field to have the basically magnetic layers, in this case the iron layers, coupled anti-parallel. And so basically what they proved is that, like, you know, when the field, the applied field is very high, of course, like the iron layer would point, like, you know, parallel to each other, and I think that I made a mistake here, so all the arrows should be pointing in the same direction and the resistance is minimum. But when you are like in zero fields, now there is like this antiferromagnetic coupling between the iron layers, and therefore the resistance reaches a maximum. So there is basically this is basically a system, you know, with two states. There is a low resistance state, which is the parallel state, and a high resistance state, which is the anti-parallel state, which is of course, like, you know, what a spin valve like exactly does. So in a spin valve, this is actually a pseudo spin valve, because as you can see, there are two ferromagnets sandwiching a normal metal. In an actual spin valve, one of the two ferromagnets is pinned by an antiferromagnet grown underneath. So in this case, you can switch independently the orientation of the magnetizations of the two ferromagnetic layers. So you go from a case where both are pointing parallel and the resistance at high fields and the resistance is low. And then when you basically start sweeping the field in the negative direction, one of them, which is the soft antiferromagnet, will switch anti-parallel compared to the previous one, and this will give you an increase in resistance. So qualitatively, basically stems from the GMR effect discovered by Fert and Grunberg. And same thing happens if you do the sweep like in the other direction. So this is the de facto, as I said, device in spintronics. But now we want to do superconducting spintronics. So what is the equivalent of the spin valve or pseudo spin valve in superconducting spintronics? Now the idea, of course, is that again, we want to reproduce this device that has two states, high resistance, low resistance, but in the superconducting state. So we have to basically replace the normal metal in between with a superconductor. Now, the physics here is not, I mean, it's different, but qualitatively you get the same effect, because now what matters is the pair breaking effect that the exchange field of the ferromagnet has on the Cooper pairs inside the superconductor. So in this case, where both ferromagnets are pointing in the same direction, the net pair breaking effect is higher, because basically these are like two vectors that you are summing to each other at the two interfaces. So you get a weaker superconductivity compared to this other case where instead you have the exchange field pointing in opposite direction. So in this case you expect a more robust superconductivity. So weaker or more robust superconductivity basically means that here you have a lower TC compared to this other situation here where you have a higher TC. So as I was mentioned before, I mean, this is for a spin singlet superconductor. If you have a spin triplet superconductors, things can change. But we will focus just on spin singlet pseudo spin valves. So, I mean, there's been work done in the literature, like, you know, to prove this. I mean, it's also before, like, way before I started, like, you know, to work on spin valves. And one of the first papers was actually this one, where they were sandwiching, like, you know, again, a superconducting metal. So it's an elemental metal superconductor, if you want, between two ferromagnets. And in this case, as you can see, the delta TC that in this talk I will define as the TC difference between the parallel and anti-parallel states was of the order of a few tens of millikelvin. In this other situation here, like, you know, this was the work done in Cambridge, like by a friend of mine at the time. So they sandwiched two holmium layers between, like, you know, niobium, and in this case the difference between TC of parallel and anti-parallel states, so our delta TC, you can see is still negative because the TC of the parallel state is lower than the anti-parallel one. So this difference has to be, like, you know, negative. It's of the order of 400 millikelvin, and this now starts becoming an interesting number because these two states are well defined, and you have two robust, like, if you want, logic states against thermal fluctuations in the system. So thermal fluctuations are certainly not of the order of half a Kelvin, so you can really think of, like, you know, encoding information associated to these two states. And of course, I mean, in the following slides, you will also see that it's possible to estimate the delta TC from this measurement of resistance in the parallel and anti-parallel states. So you apply a field that switches the ferromagnet antiparallel, measure RT. You apply another field that measures that switches them parallel and measure like RT. Of course, there are other effects that you have to take into account, like stray fields, suppression of superconductivity due to the applied field, and so on. But you can also like work out if there is a change between parallel and antiparallel if you fix the temperature and then you sweep the magnetic field. And that's what I'll show in some slides. Because if you do this, basically you can switch from one state to the other, so from one curve to the other, and you can work out basically like knowing the slope of the curve at this point, the corresponding delta Tc. So if you do like some sweeps on the transition, on the superconducting transition, and you see a difference between the parallel and antiparallel states, or some features like in magnetoresistance, then you can work out what is the corresponding delta Tc and which state is favored, like so which one has higher Tc. So I can show basically I pointed out here that in this case, like if you sweep between these two states, you can see that the antiparallel one has lower resistance than the parallel one, and in fact the parallel one has lower Tc, like than the parallel one. So in the magnetoresistance feature, high resistance means low Tc, low resistance means high Tc, and this will fall in all the slides to come. So before, like there was also some work done on ferromagnetic insulator sandwiching a superconductor. This was mentioned before, like by Alexander Bobkov this morning. And like in the idea, I mean, in this case is that they were using a superconductor, like a thinner than the coherence length. So this was a prediction done by Dejean, as Alexander pointed out. And in this case, like what you get is a full suppression of superconductivity in the antiparallel state. This work, I mean, that was done by Jagadish Mudira, like where they used europium sulfide as the ferromagnetic insulator and aluminum as the superconductor, was also then reproduced like in Cambridge, where they used niobium as the superconductor and gadolinium nitride and as the ferromagnetic insulator. And in this case, actually, what they observed was that when you go like below Tc, there is an increase, if you want, in the MH loops of the regions where the two ferromagnets are in an antiparallel state that goes beyond, extends beyond the switching fields of the two ferromagnetic layers, so the coercive fields of the two ferromagnetic layers. And they interpreted this as the superconducting condensate forcing the two gadolinium nitride layer to basically couple antiparallel, because that's the favorable question for superconductivity, the favorable situation, because in a BCS superconductor you have these spin singlet Cooper pairs. So the energetically favorable states for the system is when the two ferromagnetic insulators are pointing antiparallel, because you reduce the pair breaking effect of the exchange field at the two interfaces, as I explained before. And there was like other work as well done where they reported delta Tc larger than 0, so Tc parallel larger than antiparallel. But most of this work, I mean, was done also on oxide materials. And this was the group of like Santa Maria, Jacobo in Spain, and in this case, like the variations are small, but mostly related to stray fields, or like for other metallic system, the same thing was also seen, but related to spin accumulation. So this was the background in the literature. When I started this work, basically the point was, can we do like now these Fi, SFI, so ferromagnetic insulator sandwiching an oxide superconductor using now manganites, because manganites like give you lots of possibility in terms of choice of the ferromagnetic insulators. So I was looking at this phase diagram, and my choice went like on this material, which is praseodymium calcium magnesium oxide, for a doping of calcium of 0.2, because in this doping range it's quite stable, like in this ferromagnetic insulating phase. So I started to grow these tri-layers of PCMO, YBCO, PCMO. Now the two PCMO layers are chosen such that like we are already at a thickness where there is no mismatch in coercivities of these two layers, so they are quite thick, as you can see. And the YBCO thickness is changed between like a few, I think it was 17 unit cell, the thickest sample, down to 4 unit cell. So this was the last, the smallest thickness for which I still observe superconductivity. Now, as you decrease the thickness of the spacer, you can see that there is a broadening of the transition, and that was also reported in the literature. But these oxides, pseudospin valves, like show very sharp interfaces, so there is no mixing between the layers. So then, I mean, as I said, we started like to do these magnetoresistance measurements, and we started from the structure with 17 unit cells. So 17 means thick YBCO. And what you can see here is that now, the minimum in resistance, so the minimum in resistance, like, was basically the, no, I cannot change the pointer, okay. The minimum resistance, which means the high TC state, like, so the antiparallel state is the ITC state. And when the antiparallel state is the high TC state, so the energetically favorable state, we observe the same thing as like in the Cambridge experiment I showed earlier. So there is the emergence of these mismatch, like, sort of like increase of the region where the two ferromagnetic layers are antiparallel. To prove that this was due indeed to a proximity effect, what we did then was to insert an insulator between the two sides. So PCO is an insulator, and in this case, like, this magnetic resistance features did not appear, and the MH loop are just sigmoidal. So you can see that there is no increase in this antiparallel like region, if you want, from the MH loops. Now, for a thinner YBCO, instead in this case we observed that the parallel state is the state of low resistance, which means high TC, and when this is the case, there is no increase like in these antiparallel regions of the MH loop. So this is again also a strong evidence of the fact that you have, like, the parallel state is the state with high TC. So low resistance means high TC. So if you plot this as a function of the thickness of the YBCO, you see that for large thicknesses, mostly what you get is that the spin valve, like, prefers this anti-parallel state. So delta TC, that is defined like this, is negative. And for low thicknesses, instead, it favors the parallel state. So if you plot now this data, the delta TC, like, seen in the literature for different types of systems, with our systems, we can span, like, both across delta TC values that are positive and negative, and reach values as large as almost 2 Kelvin. So it's a very large delta TC that we observed, like, for some of these spin valves, as you can see here. So we did some control experiments. I mean, we put just bilayers in this case, like, there is nothing, there's just these V-shaped of superconductivity, suppression of superconductivity due to the applied field. We also did some other experiments. This was a parallel paper that was done by Sacho, like my colleague, where we put PCCO. In this case, the only thing we observed, like also in bilayers, not all in trilayers, was an antiparallel state favored, and this was due to the fact that there were, like, some interaction of domain walls, like in these ferromagnets with PCCO. We chose PCCO because PCCO is an isotropically gapped superconductor. It's a dirty D-wave superconductor. So we were not expecting the physics that we observed there because there are no nodal quasi-particle excitations. And again, like, the theory was done by Mario Cuoco. Very briefly, I mean, the idea is that this is the quasi-particle like excitation spectrum, if you want, for a D-wave superconductor. So it's a Dirac-like. The two exchange field at the two interfaces basically like energy split this Dirac-like quasi-particle excitation, and they generate some Fermi, some pockets of like quasi-particles at the Fermi surface. So this is the Brillouin zone. Now, each of these channels in the Brillouin zone, like, if you calculate the free energy of each of these channels, you will see like a different evolution as a function of theta, where theta is the angle between the two magnetization, depending on whether it's inside or outside the Fermi pocket. So basically, when you change the orientation of these two ferromagnets, you will get that the minimum, each channel contributes differently, and if you integrate over the entire Brillouin zone, you can determine what is the minimum of the system. Now, the point is, very briefly, is that when a superconductor becomes thick, it's like the energy of the superconducting condensate is basically favoring this anti-parallel alignment, whereas when it becomes thin, you basically have just a lot of quasi-particles in the system that are carrying the spin polarization from one ferromagnet to the other, and therefore the parallel alignment is basically favored. So this is in a very few words what's happening. And then, we also did some studies as a function of doping, because this is another thing that the manganites allow you to do. So, because there were, of course, if you decrease the exchange energy of the ferromagnet, so delta, so the superconducting condensate energy becomes larger, then you would expect that the anti-parallel state is favored. And that's exactly what we did. So I don't have a lot of time. I'll just skip through this, but that's exactly what we did. So I reduced the doping, and in this case, as you can see, you go from a state where the oops, I don't know what, I cannot change. Okay, I can go from a state where the parallel state is favored to a state when you have low doping that the anti-parallel state instead is favored. I think that the pointer is behaving very funny. Okay. Anyway, the outlook is that we proved, like, this nodal exchange coupling, like, that is possible despite the fact that the superconductor is much thicker than the coherence length along the z-axis, because, like, you have the existence of these quasi-particle states for which the coherence length effectively increases, because the coherence length is in a nodal superconductor is inversely proportional to delta, and delta becomes close to 0 near the nodes. The delta Tc values are up to 2 Kelvin, and then you have, like, a change in delta Tc as well, depending on the thickness of the superconductors. In terms of perspective, I mean, this is interesting because now you have a system where by changing the condensation energy, like, you can basically change the coupling between the two ferromagnetic insulators, and that's basically on the same line of what Alexander Bobkov was showing this morning in his talk. So on these notes, I would like to thank you for your attention, and I'll take any questions. Thank you.
Thanks, speaker.
For small energies, is there any evidence for such an effect in your experiment, or you did not find any such temperature dependence?
So you mean like that it goes from D wave, like, to become a combination of S and D?
Yeah, so it's not really pure nodal.
Yeah. Well, actually, I mean, we didn't consider this. I mean, the model of Mario just considered this nodal D wave state and its order parameter, and basically it's consistent, if you want, the thickness dependence with this idea of these Fermi pockets that, like, form on the Fermi, like, surface of the WBCO. No, we did not consider this hybrid, like, order parameter, to be honest. But I mean, we try to minimize, like, if you want, the complication of the models. But that's a good point. Yeah.
No, but if it does not appear in the data very strongly, so maybe
yeah
the case. Because there was a big controversy about this issue of D plus IS or D plus IB.
Yes.
So
note that we don't observe it in PCCO, and this is also strong evidence that if you have, because you know better than me that PCCO, like, is this a dirty D wave. We've done a lot of experiments with you. And
no, I'm not. Okay, yeah.
Yeah, we don't observe the same physics in this dirty D wave limit.
Okay, very nice.
Yeah.
Thanks.
Thank you.
Okay, let's thank Angelo.
Yeah, thank you.